Hello, this is our submission for the Da Vinci Challenge 2022. I'm Oliver Weldon.
I'm Cole Braden.
And this is Steampunk 2.0.
Hello, as I said before, my name is Cole Braden. I've been doing EV3 for several years now. I own a small business called Steampunk Robotics where I teach EV3 to young people. My hobbies also include 3D printing as well as arm wrestling.
I'm Oliver. I'm in grade 7. I first got into robotics when I got a Lego Boost set in grade 4. I love coding, Lego, and being creative. Hypothesis. We decided to use one of these little Crayola pipsqueak markers because they're small and fit really easily into EV3 with the holding design we came up with. We decided to drag the marker rather than push it because it wiggles and bounces less. We added a lift mechanism, as you can see here, so we can lift the marker up and down for when we want to move across the paper without leaving a line. We decided to put the brick on its side so it didn't interfere with the wheels at all. Procedure/methods. We initially had this angle set up, but we later opted to this one because our tests were inaccurate. After we'd run our test, we would discuss the results with each other. So we'd bounce back ideas back and forth, and we would discuss what was wrong. And if we had two ideas and we both really wanted to try them, we would try one and then the other. It was really great to only have two people. With such a small team, it's much easier to make decisions.
For testing the robot's turns, we had two basic tests to begin with. For the pivot test, which was basically we'd simply put a dot where the marker began for our robot, and then we'd program the robot to do a full 180 turn, and then we put another dot, and by seeing how close those two dots from the starting position and the ending position were together, we'd be able to tell whether the robot was turning too wide or too small. Our second turning test procedure was the square test. It's also quite simple. We would just have the robot move forward, turn 90 degrees, and repeat that 4 times. This would test both the accuracy of the turns, whether it would meet up, and the quality of the turns, whether we would leave little circles, little scratches at the corners. We got our square test, if you can see on the report, almost exactly perfect.
So we got this 180-degree test that would help us know how our angle variable was and if we were turning the right amount by driving forwards, programming it to turn 180, and driving back. And then we would be able to see if it was going too far wide, too short. We'd be able to see if it was lining up correctly. So, how we calculated our little angle variable was we took 1.1, which was approximately 90 from our calculations, and we took it and we times it by 4 to get what 360 was, because 90 times 4 is 360. Once we had our little 4.4 here, we took it and we divided by 360 to get what 1 degree was. If we had run this through the 180 test and it was not the right size, we would change it from 180 to 179, and if that lined up, or whatever direction we tweaked it in, if it lined up, we would do our little variable times the amount it lined up divided by 180, and that would be our new variable that was more precise. We start by setting our little angle variable to this incredibly tiny number, which is 0.01269177684. And it was originally a different number, but through testing and calculation and math, we eventually figured out that number, and it works quite well, and we're very proud of it. We slow down the speed of the motor second, and we specifically slow down A because the faster it goes, the more inconsistent it is, and the more it will shake, and if we go slower, it's more consistent and less likely to shove things around. When we move, we go negative because it's this way and positive is backwards. It's just the way the motors are positioned, it's flipped. We lift our pen up and down every time we turn, so we don't make a little curve whenever we turn. So we will lift, turn, and then place the marker back down and then keep going. We backtrack only on this part of the shuttle, because you can see here that we used to be going up, across, down here, and then going and doing this one and cutting across. We decided to instead go up, draw this, go lift, go backwards, and then come across and do this one. Because then the more we cut across, the more it shifts and gets messed up. Last minute changes. We had to do some last minute changes because it would start here. By the time I got to the top, it would be a train wreck, it would be totally off. We discovered it was because we had compounding errors because our left and rights were not equal. We fixed this by alternating our lefts and rights and adding pauses in between so we could finish the first thing we was doing before starting.
So, changes in strategy that we probably would have made if we were to restart. Number one, right at the beginning, would have made the robot super sturdy and stable to help with reliability.
We also should have positioned the motors differently, so positive would be forward and negative would be backwards, because there was quite a few times where I had forgotten to put the negative in and it went the opposite way and started going off-road.
Also, another thing we probably should have began with was using the same surface for each test, which is the completely flat, straight hardboard, because the different surfaces to test on can actually make a big difference to the final drawing.
Yeah, we also could have freed up more time on each of our schedules so we could have more time to work together.
Also, one of the biggest things, I believe we should have started with the angle variable sooner.
Well, it was pretty tricky, come on.
But it wasn't rocket science.
But it is rocket science.